In this video, I am going to talk about the basic concepts of bonding, and with a particular focus on ionic bonding. So, some of the objectives that you should get out of this is you should be able to understand why bonds form. You should be able to understand how ions form. You should understand why and be able to explain why the formation of ionic bonds are exothermic, and you should also be able to give the configurations of ions in the s, p, and d blocks. Furthermore, which you should already know, is how to balance charges in order to get the formula of a compound. So first, we have to look at, to understand why elements bond, we have to look at the octet rule. The octet rule basically states that elements need 8 valence electrons or, stated in a different way, full outer shells in order to be stable. So, if we look at a bunch of different elements, first we have to decide which electrons are indeed the valence electrons. So if we look at something simple like lithium, lithium has an electron configuration of 1s2, 2s1. Now, the electrons that will be on the outside are the ones that have the greatest principal quantum number. So as you see in red, those numbers are principal quantum numbers. In this case, the biggest principal quantum number is 2. So that means that there is only one electron in that principal energy level. So lithium has 1 valence electron. If we look at further down, if we were to look at sulfur, sulfur has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p4. In this case, the largest principal quantum number is 3. So, if we look at the electrons that are contained in that principal energy level, you see there are 2 and 4. So this means 2 plus 4, sulfur has 6 valence electrons. Let's go down further into something like a D block element, for instance, iron. Iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Remember, if you remember the order of all of your subshells, 3D comes after 4S in terms of potential energy. However, 4 is still a larger quantum number than 3. So in terms of which electrons are valence electrons, we look at these ones here, 4s2. So this has 2 valence electrons. The reason why that these are on the outside, even though these are higher energy, is that the principal quantum number also has a relationship to general size of the orbital. So 4s2 might be out here, whereas 3D, even though it's higher energy, might be physically smaller and still contained within the atom. And so these electrons are not necessarily interacting with the electrons of other atoms, and therefore not necessarily as important as other electrons in determining reactivity. Now, if we look at all of these different elements, 1 valence electron, 6 valence electrons, 2 valence electrons, none of these have 8 valence electrons, so none of them are stable. The only elements that will have 8 valence electrons are our noble gases. So if we look at neon, 1s2, 2s2, 2p6, it has principal quantum energy numbers. Highest ones are 2, and then we have 2 plus 6, so 8 valence electrons. This is the only one of the examples that I've just given that is stable, and therefore needs nothing else in order to become stable. Now, this might be very confusing in figuring out how elements are going to bond. So we often use Lewis structures. Lewis structures are a way of representing the number of valence electrons in an element. So if I have lithium, remember that lithium had 1 valence electron, and that valence electron was in 2s1. General format for a Lewis structure, the top 2 dots in a Lewis structure represent electrons in an s orbital. And a possible 6 remaining electrons these all represent p orbitals. So if we look at lithium with its 2s, has that just 1 electron there. So we simply take lithium and we draw 1 dot. Now, if we were to represent sulfur, sulfur has 6 valence electrons. It had 3s2 and 3p4. If we were to go back to our orbital diagrams, two electrons would be paired together. And then those 4 electrons, following Hund's rule, will be distributed in this way. Remember that according to Hund's rule, electrons will not share orbitals until all same energy orbitals are occupied. So here are our 3p electrons. So if we were to convert that to a Lewis structure, notice how these 2 electrons are together. So like the 2 s electrons that were together at top, we put these 2 together. Notice how in this box, there are 2 electrons together, so I put 2 dots together here. In these 2 boxes, the electrons are separate, so I put 1 electron here and 1 electron here. This will be very important to remember because these single electrons will give you an idea later when we start talking about covalent bonding about which electrons will be involved with bonds and which ones won't, which will give us some clues about the properties of covalent bonds and the shapes of molecules.